Hi guys, Mr. Rocco again. This is going to be the second part of a video on minerals. So how do minerals form? There's several ways that they do form. The most common method is right here. It's called crystallization. And I have a video here. I'll put a link on Canvas. It's a YouTube video. It's really cool. The gentleman does a little science demonstration how to grow some crystals, so it's pretty cool. I'll put that on Canvas. Anyway, magma is just melted, or what they call molten, which means it's in a liquid phase of minerals. So what happens is this magma soup, once it reaches a certain temperature and it starts to cool down, the liquid will start to solidify and it'll start to cool and crystallize. And usually that happens at anywhere from 600 to 1200 degrees Celsius, in that range. Magma is going to be hotter than that. It's going to be still in a liquid phase. So when magma is still in the 2000, 3000 degree Celsius range, it's going to stay liquefied. But once it reaches this 1200 degree range and drops in from 1200 back down to 600 degrees, which is still hot, but it's all relative. It's not that hot. It's going to start to cause the magma to crystallize. The rule is, and this will come up again when we talk about igneous rocks, the slower the cooling, the slower it takes this magma to solidify and become solid, the larger the crystals will grow. And then the opposite would be the faster it cools, then the smaller the crystals are. It cooled very quickly, the crystals didn't have time to grow. And so this is probably the most common way that minerals will form. They're going to come out of this liquid molten magma down under the ground. You're talking 30 kilometers, which is about 20 miles or more under the earth. And that's where this crystallization is going to start to happen. This shows a cooling procedure here. So you start with this. This is a silicate liquid. When they say silicate, they're talking about silicon and oxygen, which again, I remember the top two most abundant elements in the crust. And that's going to be in that magma. And then slowly as the magma starts to cool and the crystals start to form, you start to see crystals here in picture 2, more in picture 3. They start to lock together. They call this interlocked, intergrown crystals when they start to cool together and fuse together. You see that especially in number 5, picture 5. You can see all the crystals are starting to fuse together, and eventually you get this whole network, it says, of intergrown crystals. This is a very common, number 6 here you're looking at. This is common in rocks like a granite, excuse me, where the rocks are, the crystals, I should say, are all intergrown or interlocked together. So that's something you would look for in an igneous rock, and we'll talk more about that down the road. But yeah, so crystallization is the most common method. Other ways that minerals can form is in salt water. So you would have your seas and your oceans that are made of salt water. As we talked about in the water cycle, you're going to have the evaporation going on, which when water evaporates to start the water cycle, the water evaporates, but it does not evaporate the salt. So the salt crystals get left behind. And so what could happen is if you have a very shallow, warm sea, let's say somewhere on Earth, and the water totally evaporates away, and this is very common, you'll have salt, which is halite, or gypsum, which is also another mineral that forms in the same way, that will form from evaporation. They call halite and gypsum, these are called evaporites. So you're left with this whitish powder at the bottom of a dried up ocean or a dried up sea. And very common, this happened a lot out in western New York State. If you go out to western New York, places like Rochester, heading between Rochester and Buffalo, out in that area, you will find a lot of your salt and your gypsum comes from western New York. When I did my undergraduate work at New Paltz, SUNY New Paltz, we took a long weekend. It was like a 4-day trip out to western New York, and we actually spent time out there in a gypsum quarry. So we went out to this, and it was pure white rock. It was in the spring semester, so it was toward the end of the semester. I want to say it was like late April or early May, and there wasn't any more snow on the ground, but you walked into this quarry and it was all just pure white gypsum rock, and we watched them mine the gypsum out of the quarry. They took it back to the factory. It was really cool. Gypsum is used in a sheetrock. That's why it's called sheet rock, because that's what it is. So on your walls in your house is rock. That's what makes up your walls in a sheet form. And so if you ever, take a hammer and punch a hole in a wall and you get that white powder coming out from behind the wall, behind the paper, that's what that is. That's gypsum. And we went through the whole process. Again, they make a lot of these sheetrock out in Western New York, and we watched the whole process in the factory, from taking the gypsum out of the quarry, bringing it back to the factory, and turning it into sheetrock. It was a really cool experience. So, a lot of your salt and your gypsum comes from out there, Western New York. Another method is called precipitation. So now precipitation, be careful, it has two meanings, right? When you're talking about weather, which we just covered, that's moisture falling from the sky, rain, snow, hail, sleet, things like that. The falling is the part that you want to pay attention to when it comes to precipitation. So because precipitation means falling from the clouds, a precipitate is a very similar idea. You would have, an ocean or a sea, salt water or some kind of seawater with dissolved minerals in it. And what eventually will happen is some of these minerals and elements will settle out of the water and settle to the bottom. Oxygen, carbon, these are going to form some of they're called precipitate rocks. Hematite or minerals. Hematite is one example of that. Hematite has this reddish, silvery kind of color. It's an oxide, so it's got oxygen in it. And this forms at the bottom again of an ocean or a sea, where the material kind of settles out of the water, precipitates out. I compare it to, let's say you go to the store and you buy like a Kool-Aid or something, kind of powder mix that you're going to make, or even iced tea, but you're going to buy it in like a powder form. And then you bring that powder home and you mix it with water, right? And you put it into a pitcher and you stir the powder. You're going to make iced tea or Kool-Aid that way. But let's say you don't stir it all the way around, and some of that powder of the Kool-Aid or the iced tea crystals settles to the bottom of the glass or the bottom of the pitcher. That powder that settled to the bottom of that pitcher or water that you tried to mix it is a precipitate. And that's how some minerals form. So it's the same idea. And then the fourth method is just heat and pressure. So when we'll get into plate tectonics. When continents collide with one another, when you have volcanoes that spew lava and magma, and that magma or lava touches a mineral, it's going to melt the mineral down, and it's going to recrystallize, right? Means to do it again, right? Redo something, recrystallize. So it was already crystallized into a mineral. Now it's going to get cooked again, right? Heat. And then recrystallize to form a new mineral. So that's going to form some minerals, or even a lot of your one group of rocks, which we'll talk about, which are called metamorphic rocks. Metamorphic rocks geologists call them cooked rocks because they've been cooked with heat and pressure. So you've got your four methods let me go back. Crystallization, that's the most common, right? And this is the process here showing you the crystallizing of the minerals. You've got evaporation out of salt water. You've got precipitation, where the material settles to the bottom of the ocean or sea. And then you've got heat and pressure. So crystallization, evaporation, precipitation, and then heat and pressure. This diagram here is showing you different types of precipitates. And geologists use rocks and minerals as a sort of tape recorder and a record of Earth's history. And so what you're looking at here in this diagram is, depending on the temperature of the Earth at the time, if we were in a global warming period like you see in picture 1 and picture 3, or if we were in sort of an ice age like you see in picture 2 with this blue thermometer up top, that's going to affect what kind of precipitate you get. So basically, in simple terms, if let's say we're in a global warming period, which we are now, right? That's going to cause more of your precipitate, the material that settles out of the water, to be Fe rich. Fe stands for iron. So your iron is typically going to precipitate or settle out of the water when we're in a global warming period. And that's happening right now. More iron is settling out of the oceans. Now, let's say, I don't know, a couple hundred years from now, we go into an ice age kind of situation or a global cooling period. And that can happen. Now, instead of iron settling out and precipitating out, now you're going to have a Si, which stands for silicon. So you're going to have a silicon layer forming. And then it'll flip-flop again, and then you'll have an iron-rich layer. And that'll keep happening every time we cycle through a global warming or a global cooling. And again, geologists will come along and look at these layers at the bottom of an ocean, and they can tell just by looking at the layers. They'll this could be millions of years later. They can see, oh, here's an iron-rich layer. That must have been when Earth was in a warming period, and then we went into a cooling period. And they can even look at the thickness of the layer to tell you how long that ice age or that global warming period lasted. So it's pretty fascinating that, using rocks can help geologists determine the climate of Earth, and that's really what they use. Besides ice, and we've talked about that before, they drill through the ice caps, the North Pole, the South Antarctica, and they can use these ice core drills to tell you what the temperature was, what was the, what types of gases were in the atmosphere, etc. So it's amazing that using rocks and ice cores as a record, like a tape recorder. All right, the basic building block, and again, most minerals, I talked about this in my other video, are what are called silicates. A silicate mineral has to have, again, silicon and oxygen. And again, if you look at your ESRT on page 1, 75% of the Earth's crust is made up of silicon and oxygen. So because 3/4 of the Earth has silicon and oxygen, it makes sense that one of the most common minerals out there is a silicate, like quartz. And so the basic building block, the basic structure of most of these silicate minerals, like quartz, it's called a tetrahedron, or a silicon-oxygen tetrahedron. And what it looks like is a pyramidal shape. It has a pyramid shape. It's made of 4 oxygens and 1 silicon. And these really large ones, here's 1, 2, 3, 4. These are your 4 big oxygen atoms, and inside the middle, bonded in between, sort of in the center of this pyramid shape, is a very tiny silicon atom. So these large oxygens, there's 4 of them, and then 1 silicon make up the basic structure. That's like microscopic. The bonds between them are ionic, and I think you probably might have covered bonds, and you'll cover it again if you take chemistry, but you probably covered it with Miss Kogel. There's covalent bonds and ionic bonds. An ion is either got too many or not enough electrons. Electrons are negative charge. And so in this case, the bonds between these oxygens and this silicon are called positive ions, which means they're missing some electrons. So if they're missing some negative charge, that's what makes them positive, right? If they had too many electrons, then they'd be a negative ion. But in this case, these bonds that connect them are called positive ions. And so that's what bonds these oxygens and silicon together. So it looks like a pyramidal shape. Here's a picture of it right here. So that would be the basic structure of your silicates. It's called a tetrahedron. Tetrahedron. So you got 4 oxygens, and that little yellow guy in the middle there is your silicon. So pyramid. And then these tetrahedrons are then bonded together to make different crystal shapes. It says silicon and oxygen, again, form the biggest group of minerals. They're called the silicates. And again, that's because 75% of the Earth's crust is made of silicon and oxygen. And again, if you look on that reference table, page 1, you'll see they're the top 2 elements by mass. And therefore, that's why it makes it the biggest group. Now, this gets into more of a college level, and I wouldn't really worry too much about it, but these little tetrahedra, these little pyramids, can create, again, different structure. And this goes back to the first video of the week. It's how the internal arrangement of the atoms. These are these little tetrahedra. Every single one of these is a pyramid, each little guy here. How they're arranged internally affects the hardness of the mineral, whether it has cleavage or fracture, right? Smooth sides or uneven, and the shape. what the shape of the crystal becomes. And so these are just a few examples of the types of silicates. For example, quartz. Quartz is what's called a tectosilicate. There's really no symmetry here. All of these little tiny blue shapes you see here each one is a tetrahedron. Each one's a little pyramid, but there's no symmetry. If I draw a line vertically, horizontally, diagonally, there's no symmetry. Meaning when you take quartz, if you took a piece of quartz and you smack it with a hammer, it really isn't going to have much symmetry in it. It's going to break unevenly. They call that fracture, right, which we talked about in the first video. Now, take this one. This one's really cool. It's one of my favorites. It's called mica. Mica, all the little tetrahedra, each one of these little pyramids, set up in a nice, flat, thin sheet. And it'll be one sheet on top of the next, on top of the next. All these little microscopic tetrahedra. So it's called a phyllosilicate, sheet silicate. And that's how mica breaks. And again, I don't know if you ever were using this in middle school when you did minerals back in middle school. It breaks in very, very, very thin sheets, mica. It's really cool. And I'll make sure I show it during class time. I'll show some of these minerals here. Then you have olivine. Olivine makes what's called a nesosilicate, which is a single linked, meaning it forms in a chain, just a single chain of silicates. And then you have what's called an inosilicate, something like pyroxene, which forms a chain here too. So these are like chain silicates. They'll form in a straight line. You got a little tetrahedron, then another one, going in a straight line like that. So don't get too hung up on the types of silicates and knowing these terms over here. The main thing I just want you to take away from this slide is that different silicates form different ways, different shapes, and that affects how they break and what kind of shape they become. All right, now, the crystal shape, we're going to go over 6 basic shapes. There's actually about 30 different crystal shapes. When I took a lot of my undergrad courses, again, at New Paltz, one of the courses they had to take was called Mineralogy. It was a whole semester on minerals. Very intense course. We went over all 30 crystal shapes. Don't ask me to memorize all 30 and recite all 30 now. But there are the 6 basic shapes that you should know. I'm not going to worry about 30. So let's go through the 6 shapes. Now, why do crystals have different shapes? 2 factors. The internal symmetry. When you're looking at a mineral in 3 dimensions, you're looking at it vertically, horizontally, and then this would be coming out of the board at you, out of the screen. And then the growth rate, meaning does it grow at the same rate vertically, horizontally, and coming at you? Maybe the crystal, when it crystallized, grew faster vertically and grew slower horizontally. So how these 3 directions the mineral will grow, at what speed, is going to affect the shape of the crystal. So it's the symmetry of the crystal and then how fast the crystal is growing in these 3 directions, vertically, horizontally, and coming at you. So these are the 6 shapes in this left column here. This is showing you the length of each axis. And then this is showing you the angle that each axis makes with each other. So they don't use, in math class, right, you use, this would be the x-axis, right? This would be the y-axis. And then coming at you, like 3-dimensionally, would be z. In the world of minerals, they don't call them x, y, z. They call it a, b, c. So we're going to get rid of x, y, z. A would be like the x-axis, right, in math class. C is going to be like the y-axis. And B is like coming at you, coming out of the screen. So you've got your 3-dimension there. First shape, real easy, cubic, right? Think of a cube, right? Like Rubik's Cube. All the axes are the same length, meaning this is going to grow at the same rate, vertically, horizontally, and coming at you. A, B, C are all going to grow at the same speed. And they're all 90 degrees to each other. This would make a 90, this would make a 90, all 90s. So it would make a cube. Then you have tetragonal. Tetragonal, I call it like a cube, but take a cube and you kind of stretch it vertically. So in the case of a tetragonal, A and B are equal, meaning it grows the same sideways and at you, but it doesn't grow the same vertically. It grows actually faster vertically. So it's like a stretched out cube. If you stretch it, pull it. If you could grab a cube and pull it upwards. Again, all 90. Hexagonal. Well, you can see in hexagonal, you see hexagon, which is a 6-sided figure. So again, A equals B. So it grows the same rate sideways and at you, but again, it grows faster vertically. Two of the angles are 90, one gives you 120, which is going to give you that six-sided shape. That 120 degrees is going to give you that six-sided hexagon. Orthorhombic, all unequal, meaning A, B, C all grow at different rates. All are 90 though. So you have 90-degree angles, it's just that they don't grow at the same rate. Monoclinic, again, all grow at different rates. Two are 90. So in an orthorhombic, they're all 90. In a monoclinic, you have two angles at 90. And then the sixth one is called triclinic. These are the most very messed up, not anywhere close to symmetry. And I'll show you pictures of these coming up on the next few slides. Triclinic are going to be, again, all unequal, meaning A, B, C all grow at different rates, and you have no 90 degrees in there. There's no symmetry. All right, so let me take each one at a time here. And this is just an example, one example of a mineral that has that shape. So you have your cube, right? There's your cubic shape, right? It says not always cubed. There are many that are shaped like octahedron, octa meaning 8 faces, so you'd have 8 sides. Some have dodecahedrons. Do means 2 and deca means 10, so 10 plus 2 gives you 12 faces, 12 sides. But anyway, the basic shape is cubic, and that's halite, which is your salt. And again, I have samples of this in my classroom to show you halite. You'll see that cubic shape. This is a good example of, again, we talked about in the first video called cleavage. Smooth, flat sides. A cube has some flat sides. There's a bunch of them. I'll put X's on. So those are all faces. Each one of these is a face. So halite has that cubic shape. Tetragonal. Like a cube, but again, stretched. So this one here. So if you took a cube and stretched it vertically. Zircon, which is one of your birthstones. I'll go over those in a minute. That has a tetragonal shape. So longer in one direction. Orthorhombic. Shaped like a rhombic or prism or dipyramid. Di means two. Two pyramids stuck together. So you've got a pyramid on top, and you flip one over, and you get a pyramid on the bottom. Often look like a tetragonal, except they're not square in a cross section. Some, I've had students come in, they have these little quartz crystals on a necklace, and you'll see that sort of orthorhombic shape at the top, where you'll get a few flat sides on there, and it has that orthorhombic shape, and they'll have these, they'll drill a hole through one end of the crystal and then have it hanging on a necklace. So I've had students, with these quartz crystals. Really cool. So that's quartz, orthorhombic. Hexagonal. Sulfur is your hexagonal. So you can see the 6-sided here. So you have a hexagon on the top, you have a hexagon on the bottom, and then you're going to have a bunch of faces that have rectangles, right? So this would have 1, 2, and then you're going to add the 6 rectangles. So this would have 8 faces on it. And that's sulfur. So that's hexagonal. Monoclinic. Looks like a tetragonal, but it's been skewed. So it's almost like you take a cube and kind of push it so sideways, so it kind of slants a little bit. See if you look at that there, it's like a skewed or tilted cube or tetragonal. Feldspar. Feldspar is a really cool mineral. I have samples of that in my classroom. Feldspar has this. There's a couple different types. There's potassium feldspar, which has this is potassium. This picture. So it'll say they call it K-spar. That's like the abbreviation for it. K-spar or potassium feldspar has a pinkish color. The potassium gives it a pink color. If you crush this down into a powder and then you mix it with water, this makes clay, like clay that you would use in art class. That's what clay is made of. It's feldspar crushed into a powder mixed with water. It's used a lot in ceramics, right? Clay art class. So this is a very popular mineral when it comes to art classes. And then the other type besides potassium is called plagioclase. Plagioclase is going to have a more grayish color to it. So it won't be as pink. It's going to be more in the grayish family. But they're both used for, again, things like clay and ceramics. So that has the monoclinic. And then the one that's real, I don't have samples of this in my classroom actually. Not easy to find. It's called albite. Albite is very strange shapes. This is called the triclinic crystal. No symmetry. Like if I draw a line vertically, that's not a very good vertical line. But if I draw a line straight up and down, and I draw a line horizontally or slantwise, there's no symmetry in this crystal whatsoever. And that's what a triclinic crystal is. All right, a gem. A gem is a mineral that they take out of the earth, they mine, and then they cut and they polish and they shape it to become very beautiful and then increase the value on it. Things like, obviously, diamonds, rubies, emeralds, sapphires. All of these are examples of gemstones, which are then used in a lot of your jewelry, necklaces, rings, earrings, etc., bracelets. And so that's what a gem is. A gem is a mineral. It's just taken out of the earth in its natural form, and it's going to look very dull and very scratched and dirty, and they're going to clean it up, they're going to polish it, they're going to shape it, and they're going to put it into jewelry and stuff, and that's going to increase the value. And then you have your birthstones, and these are just an example. There's probably other birthstones. Some of you might know your birthstone, but these are some of your birthstones for each month. Some months have multiple birthstones, others don't. So January is going to be your garnet. Again, a lot of these are gemstones, so you've got that reddish color, the garnet, if you're a January birthday. February is your amethyst. That's basically quartz is what amethyst is. It's just a purple quartz. So that's your amethyst. March is kind of cool. It's called a bloodstone. So that's a bloodstone. Or aquamarine, which has that bluish aqua color. My birthday is April. Some of you might be in the same month as me. So we are the diamond in the rough. Thinking to the movie Aladdin, right? So diamonds is April. May, if you're a May birthday, you're an emerald. You have that beautiful greenish color. June is either a pearl or a moonstone. That's kind of cool. So June birthday, some of you have a June birthday. You got that moon. You can see almost like that quarter or crescent moon in there. Really cool. Moonstone. I like that one. July is your ruby, right? That's another one of these reddish gems right there. August is a sardonyx or peridot. It's got this greenish color. There's your peridot. September, I like this one too. It's called lapis lazuli. It's just cool to say it. Lapis lazuli is this really like awesome looking bluish color. Or sapphire. Again, both are the month of September. October, this is another cool one. You got this opal. It's got this like rainbow, iridescent rainbow color to it. Really neat. I like opal. Or pink tourmaline. That's also pretty. November, you've got topaz, which can be blue or yellow. Citrine is going to be more of a yellowy kind of topaz. Or you could have a blue topaz. That's November. And then December is, again, turquoise, which is that bluish. Or this one here, zircon, which is also this bluish gemstone here. So these are just examples of some of your birthstones. All right, and finally, I just go over this just for fun. When you look at a diamond, there are the 4 C's of a diamond. And I don't know if you know the 4 C's. To look for a good quality diamond, and this I had to, and being an earth science teacher and having taken a lot of classes on gems and minerals helped me to have a little bit of an edge when it came to picking out the proper ring, engagement ring for my wife way back when. And you want to look for the 4 C's. So I'm just going to briefly go through this real quick. I love the got bling. So the first C, when you're looking at the C's of a diamond, is color. And color is they're going to use the alphabet. There's no A, B's, and C's. Don't know why. I still haven't found an answer to that yet, but they start with D. So there's no A, B, C color. Diamonds will start with a D. Colorless. So if you were to look for an engagement ring or even just a diamond, you want to buy a diamond necklace or a diamond, earrings. D, E, F are nearly colorless. Obviously, you're going to pay top dollar. And then you work your way down the alphabet, G, H, I, J. My wife's engagement ring, which I bought many, many years ago, is H. So it's a pretty good, clear diamond. The main stone. It's got a center stone around and then stones on the side. But anyway, D, E, F, going to cost you big bucks. G, H, I, J, if you know what you're looking for, you can get a decent price. Then you work your way down. KLM, now the diamond's starting to turn more yellowish color. NOPQR, you're getting really into the yellow range now. And some people like a yellow diamond. I mean, there's people, it's personal preference. Then you go Z, S to Z, and you're talking very yellow. And again, a Z ring, diamond's not going to cost you much. So if you're looking for the cheapest diamond, go with the Z. But that's color. The second C is called clarity, how clear it looks. It says an accurate clarity can only be assigned by an experienced, professionally trained grader. So, you have to be like a gemologist. And they use they call it a loupe or a magnifying glass at 10x. So you don't want to use more than 10, not less, but 10x. You have FL, again, going to cost you huge amount of money. FL stands for flawless. There's no inclusions. So what happens is these diamonds, I don't know if you're familiar with it, diamonds form down deep in the earth, especially in the volcanoes. That's where they typically form. Most of them are coming out of countries in Africa. And so you have these African nations where these volcanoes are, where the diamonds will form way down deep. They crystallize, right? We talked about crystallization. And then all of a sudden you'll have a volcanic eruption where these diamonds just kind of get exploded out of the volcanoes. Sometimes they have to go down deep and dig for them, but many of them just come out during eruptions. What happens is as the magma is crystallizing, you will get little inclusions, little specks of dirt get into the diamond as it's cooling and crystallizing. And you don't want that. So flawless means no inclusions whatsoever. It is like crystal clear. Again, you're going to pay top dollar. Then you have your VVSs, VVS1, VVS2, which stands for very, very slight inclusions. Hard to see, very hard to see. Again, top dollar. Then you have your VS1s, which are very slight inclusions. Again, not easy to see, VS1, VS2. You might have you can see that in this picture, a little tiny speck in there. Under a loupe or under a magnifying glass, you might see it. Looking at it with the naked eye, hard to see. My wife's ring, and again, I'm trying to remember off the top of my head, I want to say her main stone is a VS1. So very hard to see any inclusions in there. Then you have your SIs, which are also decent, slight inclusion. You might see a few little specks in there, little pieces of dirt that got into the diamond as it crystallized. And then you got your Is, I1, I2, I3. So you can really start to see, inclusions very easily. You don't even need a magnifying glass and they'll start to show up. Again, you're going to pay less money, but, you get what you pay for. So those are your Is. Now, how the diamond actually handles light. When they talk about bling, right? What do they mean by bling? You want the light to go into the top of the diamond, come in the table. This is the top. You want the light to come into the table, bounce around inside this diamond, but when you want it to you want the light to come right back out the top. And how the diamond is cut is going to be critical to determine if you get bling or you don't get bling. So basically what you want to do is, and this is what they do, if you go down to places like Manhattan in the Diamond District, they will lay out a bunch of diamonds on a little felt pad on the counter. You want a light directly above your head. You want some kind of light above you. When you pick up each little diamond, you want to get blinded by that diamond. You want the light coming off the diamond to come right back in your eye. If it doesn't blind you, it's not a good diamond. If it's kind of dull, that's a bad diamond. And it was cut probably in a bad way. So there's parts of a diamond. Again, the table is the top flat part. Then you have the crown. The crown is the upper half of the diamond, this part. You have the pavilion. That's this whole bottom section. You have the cullet, which is this little bottom point of the diamond. And then you have the girdle, which is the part between the crown and the pavilion. If it's cut really well, again, the light's going to go in. It's going to bounce around all these facets, they're called. And then that light's going to come right back out the top, right back out the table. That's a well-cut diamond. And that's what you want. That's why they say, oh, you're wearing a lot of bling, right? You want it to bling. Because if it doesn't bling, then it's not a good diamond. If they cut this pavilion, you can see the difference in the picture. If they cut this one in the middle, see how they cut it too deep? That means the light is going to go in, but you see it's going to escape out the bottom. It's going to come out the side. It's not going to come back at you. That's not good. Or they cut it too shallow. Same thing. the light isn't going to come back out the top, it's going to go out the bottom. So it's really, and this is a craft. These diamond people that cut these diamonds, amazing. I mean, takes years of practice, and they learn eventually over time, cutting diamond after diamond, how to cut that diamond just right so that light doesn't go out the bottom, comes right back at you to give you that bling. And that takes a lot of skill. So you got your clarity, you got your color, you got your cut, and then you got your final thing, which is carats with a C. Quarter carat isn't, that big. Half a carat's not that big. 3/4 getting much bigger. 1 carat, says here, equals 1/5 of a gram. Okay. And then a carat is divided into points, 100 points. So if you have a 3/4 carat diamond, weighs 75 points, or 0.75. Right? So that's how you determine the carat. It's divided into 100, and then 3/4 mean you have a 75 point diamond. Probably you want to at least look at something like a carat. A carat is a decent size. Once you get above that, the diamond will get even bigger and bigger and bigger. I mean, you're talking about your celebrities. I'm thinking of people like J-Lo and stuff like that. They're gonna have, if you ever see, a lot of their rings and engagement rings and stuff. They're gonna have diamond rings that have, 6 carats, 8 carats. I mean, that diamond is like huge. It gets very gaudy, and it's even too big for the finger. It looks funny. I would say a decent size is a carat. That's a good size. Carat and a half. That would be like the top end, I think, for most people. Once you get into 2, 3 carat, I mean, that's getting into a decent size, and also, of course, bigger price. So that can be a problem. And then the other thing is how it's cut. When it comes back to cut, depends on, it's really personal preference. Round is probably the most popular. Round is also going to cost you the most. And again, my wife's ring has a round stone in the center. The reason round costs the most, when you have this chunk of diamond, it's going to be an irregular shaped diamond. The first cuts they have to make out of that big piece of diamond are the round. So they're going to cut a bunch of round stones out of this chunk of diamond. Then you can get like something like a marquee. That's this one here. You could get that out of the edge. So they could take the leftovers and start to get the edge and get the pear shape or the marquee shape from the edges of what's left. But the most expensive, and this is just talking to diamond people down in Manhattan. I made many trips down there to the Diamond District and talking with the men and women down there. The round, they'll tell you, is always going to cost you the most money just because that's the first cut that has to be made out of a chunk of diamond. Ovals and marquees and pears, they can get that with the leftovers. So you can pay less money if you don't mind having any one of these shapes. Probably the shape or the cut goes with the times. It's like there'll be fads, for so many years that round will be popular, then that might go away. People might then all want oval. Princess is a very popular one, I think, right now. A lot of people like the princess cut. But yeah, it's really personal preference. You have your oval, your marquee, your pear shape, heart shape, emerald shape, and then radiant. This one's really sparkly. That's probably popular too right now. Everyone wants that bling. So those are your 4 C's. You got the color, the cut, the clarity, and the number of carats. And so that's a little a little background on the 4 C's. So this way you have that information. All right, and that's it for this video, and I will talk to you soon.